Hello, in this video we're going to take a look at geostationary satellite orbits around planets, particularly the planet Earth. Now, what is a geostationary satellite orbit, you might ask? Well, a geostationary satellite orbit is one in which a satellite that is orbiting the planet or the Earth always remains above exactly the same point on the planet. It never, its line of sight never moves away from that. It's always directly overhead, over that same point on the planet perpetually. Now, the question asked here, what is the radial distance from the centre of Earth of a geostationary satellite orbit? Well, for a satellite to remain in geostationary orbit, it has to have a particular radial distance. It can't be too large a radial distance and it can't be too low a radial distance. It has to be a specific value, and that's what we're going to try and work out. So let's start by drawing a diagram, because we need to consider first the forces at the surface of the Earth. Now, if we draw the Earth with a point mass on its surface, we'll call that little m. And we assume that all the mass of the Earth is concentrated at its centre. Now, Earth has a radius, which we'll call small r. And between the point mass and the centre of the Earth, there is a force, which we'll just call F. But F has two forms, and one of the forms is due to the mass's weight, which is mg, which we'll call equation 1. And form 2 is due to gravitation, which is g, big M, little m, over r squared. Big G is a gravitational constant. I'll just point properly with the pointer. So G is a gravitational constant. Big M is the mass of Earth. Little m is the mass of the point, mass on the Earth's surface. And r is the distance between m and the point mass. So what we'll do is we'll call that equation 2. And in order to derive a relationship between equations 1 and 2, we recognise that they must be equal for a mass, a stationary mass, on the surface of Earth. So for when I say a stationary mass, the mass on the surface of Earth is stationary relative to the Earth, but of course the mass is actually travelling in space because Earth is turning. So what I'll do is I'll just write down then that mg equals g m over r squared. And if we call this, well, first of all, we won't call it anything. We'll just move that up a little. And what you'll be able to see is that we now have two masses on either side. The mass of the single point on the surface of Earth, which cancels. And this leaves us with G equals gm over r squared, which can be rearranged to make gm the subject and that is equal to g r squared. And we'll need that equation, we'll call that equation 3. Yeah, we'll need that equation for what we're about to do next. So I'll just highlight that in blue, and then I don't miss it when I want to look back later on. So there we are. Now, we now consider satellite. Right, okay, so let's draw another diagram. If I draw a circle, and again we assume all the mass is concentrated at the centre of Earth, and we've got this time the mass of a satellite, but we'll still call it m, because it's because the mass of Earth is all concentrated at Earth's centre, then you can assume that the mass of the satellite is that point mass on the surface of Earth. But of course, the situation is a bit different, and the radial distance is different as well. So let me just draw in the radial distance, which is this time labelled as capital R. So if you think about it, when you're considering the Earth satellite system, then Earth would normally have its boundary around here like that, so that would be little r, that would be lowercase r, that distance there. Now again, for the satellite, let's mark this in blue. For the satellite, there is again a force acting towards the centre of Earth. So first of all, we have to recognise that this time F is not equal to mg, because g is different from what it was in the first part. Obviously the gravity at a further distance from Earth will be less than it is for a mass closer to the surface of Earth. So we cannot write that down in this case unless we use a different value for gravity. But that's not the gravity that we are really considering here. So we've got still two forces, but the equivalent force to F equals mg is actually F equals mv squared over big R. And V, let me just scroll up a little bit, is actually whoops, let me just cross that out. There we are. So V is the velocity of the satellite, and it's actually the tangential velocity, and we take it to be a scalar. So let me see, how many equations have I listed? So we're on to equation 4 now. So this is equation 4, and again, as with the first part that we did, there is a gravitational force, and that is G big M little m, but unlike the first part, this is also divided by big R squared. Now we'll call that equation 5. there we are, equation 5. Because, and it's the same for the point mass in the first part, because the satellite is always, can't spell to save my life, can I? Always above the same point on Earth, then we can equate 4 and 5. So we get mv squared over big R equals g big M little m over R squared, big R squared. Now, as before, you can see that you can, let me just do that again. You can see that the m's cancel and one of the r's cancels on both sides. And that leaves us with v squared equals g m over r. But what we now want to do, because we've got to assume that we don't know what big G and the mass of Earth actually is. You know, suppose you're on desert islands and you don't have access to facts like that, then you would have to know what to do with this equation, for example, to work out the velocity on the left hand side. So I've forgotten what equation we're up to now. So we're up to equation 6. And what you will notice is that we actually found what Gm was in this equation here, and that's gr squared. So what we do is we say from equation 3, Gm equals gr squared. So, and I've forgotten again what that last equation is labelled as. It's 6, isn't it? So equation 6 becomes v squared equals gr squared, all divided by r. My memory is really bad. And guess what? I'm on thiamine for it as well. It's supposed to preserve memory, but not seemingly doing a brilliant job. Okay, so v squared equals gr squared over capital R. But the problem is, big R is what we want to work out. But now we've got velocity and we don't know what the velocity is. But can we work it out? Well, yes, we can. So let's consider the satellite orbit. So this is the satellite, and it's going round in the orbit at velocity v, and the mass of Earth is at the centre, and we know that the radius is r. So because it's a circular orbit, and I'll write this in green, because the orbit is circular, then in one cycle the satellite covers a distance of 2 pi big R meters, we'll call it. Now then, this means that the satellite's orbit, I'm making some, there we are, orbit, no, still can't spell, satellite orbit, actually it's wrong again. Let me just go down. Do excuse me for these little errors. So this means that the satellite's velocity V is, and we'll highlight this in blue, V equals 2 pi R over T, where T is time, or time period. Right, so we'll call this, and I've forgotten which equation we're up to again, so that's 6, and this one's equation 7, and we'll call this equation 8. So substituting equation 8 into equation, and I think it's equation 7, isn't it? We get let me see, I'll there we are, Control C. I hope this works. I'm cutting and pasting. No, it doesn't work, but never mind. We've got velocity squared equals GR squared over big R. So substituting equation 8 into equation 7, we get 2 pi big R over T all squared, and that's equal to GR squared over R. Just keep the top on that. There we are. Right, so okay. So we can square the left-hand side. So we get 4 pi squared R squared over T squared. And that's equal to G R squared all divided by R. And if you've done GCSE mathematics, you should be able to figure out that R cubed is equal to G R squared T squared over 4 pi squared. So we've just multiplied both sides by t squared and r squared. Sorry, I'll start again. We've multiplied both sides by t squared and r, and then we've divided both sides by 4 pi squared to get this expression here. Now, I'm going to cut and paste that. I somehow don't think it's going to cut and paste very easily, but let's see if we can do it on the next page. So there we are. Gives us a bit of room. So we know that gravity G equals 9.81 meters per second squared. We know that the radius of Earth is 6.4 times 10 to the 6 meters. And we know how long it takes the orbit of the satellite to complete one revolution, and that is just 1 day, because it's always above the same point on Earth. So as that point goes round the circumference of the Earth, it does that in 24 hours. So does the satellite. So T equals 24 times, so it's 24 lots of 60 minutes times 60 seconds. And that, and I have to do this on my calculator, is 24 times 60 times 60, which is 86,400 seconds. That's the time it takes the satellite to go to complete one revolution. So what we can do now is work out the radius. So we've got r cubed is equal to 9.81 times r squared, which is 6.4 times 10 to the power 6 all squared, times, have I done it right, times t squared, right, 86,400 all squared, divided by 4 pi squared. Now I'll have to work this out my calculator. So here we go. We've got 9.81 times, in brackets, 6.4 times 10 to the power of 6 all squared, close bracket, times 86,400 all squared, close bracket. So on the top we get 3.0 times 10 to the 24 divided by 4 pi squared, which I'll just leave like that. And if you divide that out, we get r cubed is equal to 4 pi squared is equal to 7.598, we call it, times 10 to the 22 meters cubed. But we want it in meters, so taking the cube roots of both sides, we have well, I'll write this down for you because you express a cube root as r equals, put a little 3 there, 7.598 times 10 to the 22. We'll put the meters cubed inside the square root sign. This is the same as on your calculator working out 7.598 times 10 to the 22 meters cubed, all to the power 13. In your calculator, you wouldn't put this meter cube bit in here. That's really just my pedanticism, if you like, you know. But on the calculator, you would type that out in brackets and then find the 1/3 root. So that comes out to be equal to, and I'm just going to put this into my calculator memory. So if we find the 1/3 root of that, then we get 42, what is it? 42,354,434. So 42,354,435.83 meters. This is the same as R being equated to 42,354 point, that's a point, a decimal point, 436 kilometers. And that is the answer. So I just wanted to point something else out regarding this expression here, which I didn't label again. I'll call it equation 9. So with equation 9, that is basically Kepler's law. And you'll note that if I just write it here in blue, or no, I'll write in green. This is Kepler's third law, effectively, which states that the cubes of the distances are proportional to the squares of the periods. And likewise, some people also say that the squares of the periods are proportional to the cubes of the distances. They're exactly the same thing. And the constant of proportionality is just this gr squared over 4 pi squared. And that's all it is. That is Kepler's third law. So we've gone from the very basics to work out Kepler's third law, and then we've substituted in our values to work out the radial distance that a geostationary satellite needs to be at, needs to maintain for it to stay in that orbit. So I hope you've enjoyed that and learned something from it, and that you will come back and watch more of my videos. I we'll bid you farewell for now and look forward to seeing you soon. So bye for now.